Okay, let's unpack this. Welcome to the deep dive.
Oh,
Have you ever been in calculus class, maybe, wrestling with integrals and just thought, am I ever going to use this stuff?
happens all the time.
Well, today we're actually diving into some sources that show this really strong link between, well, that math and the real world of forest resources technology.
Yeah, we've been looking at material connecting integration, that core calculus concept, to understanding actual physical systems,
Oh,
specifically forests.
exactly. So our mission for this deep dive is to explore one really specific, really important application. Basically, how integration helps calculate something crucial for understanding the environment.
And we're framing this especially for you. Maybe you're that college student kneed up in calculus right now, wanting to see where it clicks in the real world.
So the main thing our sources are pointing to is using integration right there in forest resources tech to figure out the total carbon stock over a given forest area.
Total carbon stock. That sounds big and complex. How do you even get a number for something like a whole forest? And yeah, why integrate? Why is that the math tool you reach for?
Like for finding a total amount of something, carbon in this case, that's spread out and,
Yeah.
well, it isn't the same everywhere, right? It's over a whole area.
Well, the fascinating thing, and this is what integration really unlocks, is how you handle that variability. Carbon stock, the carbon in the trees, the soil, the undergrowth, it's definitely not uniform.
No, of course not.
It changes all over the place. Depends on the tree species, how old they are, how dense the woods are right here versus over there, the soil type, it's constantly varying.
Right, so you can't just like measure one tree or one little patch and multiply it out. It wouldn't work.
Precisely. And that's where integration just shines. It is the mathematical tool designed for summing up quantities that are continuously spread out and changing over space or time. Think about your double integrals over some region R you study in class. You're essentially taking a function, let's call it fxy, and that function represents the density of carbon, maybe tons per square meter, something like that.
At every single point, XY within that forest area are.
Yeah, and fxy changes value depending on where you are because, well, the carbon varies.
Okay, yeah, I think I'm following.
So the integral of that function, fxy, over the whole region are that fxydA thing you work through. That's the mathematical way to add up the carbon in every single tiny piece of area, that dA. It does that across the entire forest section you care about. It lets you go from knowing the carbon amount per unit area everywhere,
Which varies.
which varies, exactly, to knowing the total carbon for the whole defined region, no matter how much it changes inside that boundary.
Okay, that connection clicks.
Yeah.
It's taking that math concept, summing up infinite tiny bits and slapping it onto a real physical space.
Yeah.
But, like, how do foresters get that function, fxy, or the data points they need for this in the real world? It can't be perfect.
No, it's not perfect, but that's where the technology and the field work come in. They don't usually measure every spot. That'd be impossible.
Yeah.
They use methods like setting up sample plots. They measure carbon density carefully in smaller representative areas. Or increasingly, they use remote sensing data.
Like satellites.
Satellites, aircraft, yeah.
Yeah.
Stuff that can estimate forest structure and biomass over huge areas. And that data can then be correlated, linked to carbon density on the ground.
So they build models from that.
Exactly. They use this data to build models or maybe create maps of carbon density across the forest. These models, or data grids, they essentially give you the information needed to do the integration, sometimes analytically if you have a nice function, or more often numerically if you just have a grid of data points.
Wow. Okay, so the data from, like, boots on the ground or eyes in the sky becomes the input for the calculus. That makes it way more concrete than just summing tiny pieces. So, okay, they do all this work to get this total carbon stock number for a forest area. Why? Why is that number so critical in forest resources or for understanding the environment generally?
Well, connecting it to the bigger picture, forests are just fundamentally important carbon sinks, right? They soak up enormous amounts of CO2 from the atmosphere.
Huge amounts.
So knowing the total carbon stock of a forest is, well, fundamental for monitoring climate change, for assessing how much carbon a particular forest is actually sequestering, or evaluating the impact of logging, or maybe a conservation project.
Carbon credits too, I guess.
Carbon credits, definitely. It's a key metric for managing forests sustainably and really understanding their role in the whole global carbon cycle. And you can even use related math, differentiation, to look at the rate of change.
How fast it's changing.
Yeah, how fast a forest is growing and absorbing more carbon, or maybe losing it due to disease or fire.
This really brings it home for you, the listener. When you're sitting there, struggling with the bounds of a double integral, or figuring out how to integrate some messy function. This is where it lives and breathes. Your work isn't just symbols on paper. It's literally the language we use to quantify and understand these complex, vital environmental systems. It gives us the precise tools to turn messy, real-world data into meaningful totals.
Yeah, it's powerful stuff.
So wrapping up this deep dive, the sources clearly show integration isn't just a test question. It gives us a concrete, really essential way to calculate total amounts of resources like carbon stock across defined areas, even when those resources vary a lot.
It's about taking something continuous and variable and accurately summing it all up to get that crucial big picture number.
And maybe a final thought to leave you with. Beyond just forest carbon, where else might finding a total quantity over a space, or maybe over time using integration, where else might that be absolutely essential?
Yeah, think about, I don't know, electric fields or total force from pressure, maybe fluid flow, even probability distributions. Where else is this idea of summing up distributed pieces totally indispensable, something to mull over?